welcome to the course on Introduction to Electrical Engineering. We have a lecture 42 today on electrical measurement part 3. We will starting with the outline of today's presentation with the introduction and DC power measurement, electrodynamometer type wattmeter, induction type wattmeter, AC power measurement, energy measurement, single phase induction type wattmeter, exercise and numerical, and followed by references. So, we have a starting with the introduction, we have this power. We define this electric power is the rate per unit time at which the electrical energy is transferred by an electric circuit. Power calculation depends upon the circuit source and the load connected. And in case of direct current, that is DC power, we call it the power drawn is denoted by the product of current and voltage, that is P equal to V into I watt. And of course, in case of alternating power, that is AC power, AC power is subdivided into 3 parts. First is the active power or real power, or we call it true power, that is normally we already discussed P equal to V I cos phi cos theta, and unit is watt. And the second power we call it apparent power, that is your typically reactive power, that is Q, that is V I sin theta VAR, and the apparent power, that is S equal to V I, that is called V A, and this is what we call it the power triangle. So, S is the apparent power and y axis is active power, and you can call it perpendicular is called reactive power. And power factor we define the terminology here, that is P real power divided by S, that is apparent power. So, by coming to the definition of like active power, that is the capacity of the circuit for performing work in a particular time. Apparent power, it is a product of voltage and current, and reactive power, it is the resultant power in VAR of AC circuit when current waveform is out of phase with the waveform of the voltage, usually by 90 degree if the load is purely reactive and a result of either capacitive or inductive load. Then we define the power factor, it is the ratio of the real power flowing to the load to the apparent power in the circuit, and it is a dimensional less number. So, coming to the typically the instrument like wattmeter, it is an instrument for measuring the electric power or the supply rate of electrical energy in watts for of any given circuit. And the energy meter, the meter which is used for measuring the energy utilized by the electric load is known as the energy meter, and the energy is the total power consumed and utilized by the load at particular interval of time, and it is used in domestic and industrial AC circuit for measuring the power consumption. Now, coming to the application, we have analog wattmeters, as you can see, of 3 different kind, but you can see the scale is a kind of analog scale like then you have a digital wattmeter, you can discriminate what is the difference between that and this. So, you are finding directly the in digital wattmeter like, and this is analog energy meter, as you can see the analog all this analog quantity on analog meters, and of course, the number is coming from the movement of the disc here like. Then you have a digital energy meter, as you can see all the digits here, which measures the typically the energy in kilowatt hours like. Or digital wattmeter for domestic appliances, typically the concept have gone for the concept of a smart grid. You can even measure the power for every domestic appliance, which really the energy gadget in the home, whether it is your air conditioner, whether it is your refrigerator, or it is your typically washing machine or TV, the big gadgets which really have. So, they can easily, you can measure the power of it digitally, because that is we require virtually for the purpose of, you can call it like a smart grid like, or this typically a radio frequency power meter. The whatever the power, it goes through radio frequency to the computers, and typically this concept has come now most of the application that person need not to come even to measure the energy meter reading. It can go by radio frequency to already through the network through. You can put a kind of fan in a locality and then take a reading from all the houses through these meters like. Or there is a power analyzer, you can just see how you can see not only the all 3 kind of voltage, current, power, but you can even see the phase and all that. As you can see the meter in your 3 phase power analyzer or single phase power analyzer. or you have a like a smart energy meter which I was mentioning, that it takes care of typically all the measurement in the houses for different appliances, like, or your electric vehicle energy meter, I mean for the charging you use it. So, it is account for how much energy really you have taken up for the purpose of charging from the charger, like so you can see the clear display for the of this electrical vehicle charger energy meter. Then you have a, I mean on similar line you have a smart gas meter. The concept of smart gas meter is again that whatever the reading you are taking is already getting communicated through and it is accounted in the communication system. Then you have a smart metering communication system which I was mentioning, that you are taking the your wide area network, all the data are going from different houses or different appliances, the reading of all these, I mean to the network, like now coming to typically example of DC power measurement. The DC power measurement, the power can be determined by using voltmeter, ammeter, by connecting them anywhere in the given arrangement, as we will discuss, and the power can be calculated by product of the reading of voltmeter and ammeter. And typical example is here that you have a DC source like a battery, you have a ammeter and voltmeter, and then you have a load. So, or you can have a voltmeter after the ammeter, or you can keep the voltmeter towards the source, or you can keep the voltmeter towards the load. So, maybe that is small, because these are the typically analog instruments. So, that may consume little power. So, that power how we account for, and what kind of the circuit, which kind of the arrangement of the measurement of power which will need, that is also important here. So, coming to the method 1, in figure A which is shown here, the voltmeter is connected between the load and ammeter. The ammeter indicates the current through load and voltmeter. The ammeter reading is your IL plus IV, and IL is the load current, IV is the voltmeter current, and RV is the resistance of voltmeter. So, power consumed by the load will be V into IL, or V into I minus IV, or V into bracket I minus V upon RV, or that is V into I minus V square RV. So, you can call it the power consumed by the load is equal to power indicated by the instrument minus the power loss in voltmeter. Now, coming to the method 2, in typically figure B, where the voltmeter is connected towards the source. So, ammeter is connected between the load and wattmeter. Voltmeter indicates the voltage across the load and ammeter. So, V equal to V A plus V L, and the voltmeter reading is V. The voltage across the load, voltage across the ammeter is V A, and voltage across the load is V L. Now, the power consumed by the load will be V L into I. So, that will be V minus V A into I, or V into I minus V A into I, or V into I minus I A square R A, or you can call it the power consumed by the load will be equal to power indicated by the instrument minus power loss in the ammeter, like. So, in both method, power indicated by the instrument is equal to the power consumed by the load plus the power consumed by the instrument nearest to the load terminal, whether voltmeter or ammeter, like. So, method 1 is used for low resistive load power measurement, and method 2 is used for high resistive load power measurement, because that will not cause the error to increase more than particular. Now, coming to AC power measurement, the power measurement in single phase AC circuit. So, you can call it electrodynamic wattmeter, I mean which called EDM in short, or you have a induction type wattmeter. So, these are the two different kind of wattmeter, because here we have a concept of power factor. So, certainly in AC circuit we have to use the wattmeter. Simple voltmeter ammeter reading will not give the power measurement correctly. So, coming to power measurement in 3 phase AC circuit, we can have either 1 wattmeter method, 3 wattmeter, or 2 wattmeter method. So, coming to first a single phase AC power measurement. So, power measurement in single phase AC circuit. So, it is a electrodynamic wattmeter, that is EDM wattmeter or induction type wattmeter. So, coming to first electrodynamic type of wattmeter, which is quite popular use. So, there are 2 coils are connected in different circuit for the measurement of power. So, fixed coil or filled coils are connected in series with the load and carry the current in the circuit, and the moving coil is connected across the voltage, and therefore, carries a current proportional to the voltage. And since the moving coil carries the current proportional to voltage, it is called the pressure coil or voltage coil, and moreover it has a very small current. So, that is why we prefer to have a very small current in moving coil, and typical example is here. So, this is the typically, and this is the circuit. So, you have a fixed coil which is in 2 parts. So, current is a virtually current flowing through this. So, it is connected in the series, and we have a very less resistance, and this pressure coil which is connected in across the line that is moving coil. So, that it should not take any large amount of current, virtually it should take a 0 current like practically, but there will be any current because this resistance is quite large here. So, that is the typically the component of your electrodynamic type of wattmeter. So, now coming to the fixed coil, the field required for the operation of instrument is produced by the fixed coil, and the coilers are divided into two sections, and the coils are air cooled and carry current of the circuit, and these coils are wound with the heavy wire. So, now coming to moving coil, the mounted on a spindle and entirely embraced by the fixed current coils, and moving coil as pressure coil. So, a series resistance is put in to limit the current of around 10 to 50 milliampere. And now coming to like a typically of construction of this electrodynamic wattmeter. So, there is a like what we discussed already in the last class for the ammeter voltmeter different instrument. So, here also similarly we have a controlling torque, that is spring control is used for the instrument, and the spring acts as lead to the moving coil, and the damping torque, the air friction damping is normally used, we discussed already in kind of dynamometer instrument. So, moving system carries a light aluminum vane, and the scale and pointer, the mirror type scale and knife as pointers to remove your reading error. So, instruments hysteresis torque of an electrodynamic instrument is your Ti equal to I1 into I2 into dm upon d theta, where I1 I2 are the hysteresis value of current in the two coil as it is shown in case of in the figure like now. So, we can say for DC operation, the DC current in both coil, the torque can be as T equal to I1 I2 into dm upon d theta, and at controlling torque is provided by spring. So, that is I1 I2 dm upon d theta equal to k into theta, or you can call it theta equal to I1 I2 into dm upon d theta divided by k. And for AC operation, the average deflecting torque over one cycle is Td equal to 1 upon T 0 to T Ti into dt, and Td equal to dm upon d theta, that is 1 upon T 0 to T I1 I2 into dt. And if the current in both coils are equal to, let us say for AC operation, that is I1 equal to I1 sin omega t and I2 equal to Im2 sin omega t minus phi, then we can say deflecting torque will be your Td equal to dm upon d theta, that is 1 upon T 0 to T Im1 sin omega t into Im2 sin omega t minus phi into dt, and that is equal to I1 into I2 cos phi into dm upon d theta, where I1 I2 are the RMS value of two currents, where I1 is Im by M1 by root 2 and I2 equal to Im by root 2. So, in the pressure coil being a purely resistive, so we can say I2 equal to V upon Rp, and for spring control we can say this is I1 into V upon Rp cos phi into dm upon theta equal to k into theta. So, theta comes from here I1 into V upon Rp cos phi dm upon theta divided by k, or theta is proportional to your P. So, that we can say shape of the scale for the electrodynamic wattmeter, the reflection is directly proportional to the power, and scale is uniform over the range in which dm upon d theta is constant over 80 to 100 degree, as you can see here, and nature of the scale of EDM type of wattmeter. So, that is in typically power measurement in the linear range. Now, coming to typically you can call it the electrodynamic wattmeter errors. So, first is the pressure coil inductance effect, well large number of turns are there in the. So, here is the phasor diagram. So, we have a voltage applied for pressure coil, then the current in the pressure coil at the angle of beta because of inductive effect, and then the your typically the current in the your current coil with the angle of phi between, virtually that will be 5 factor angle. So, ideally current in the pressure coil is in phase with the applied voltage, but pressure coil inductance lead to a phase shift in the voltage and current, and from figure we can call it beta, that phase shift between pressure coil voltage and current will be beta equal to tan inverse omega L upon R, and you can say angle between current in the current coil circuit and pressure coil circuit is alpha equal to phi minus beta. So, the actual wattmeter reading will be or V upon Zp into I1 cos alpha dm upon dt upon k, and you can call it that will be equal to V upon Zp into I1 cos phi minus beta dm upon dt divided by k, where Zp equal to Rp upon cos beta, and actual wattmeter reading that is equal to V into I1 cos alpha dm upon theta divided by Rp into cos divided by cos beta into b k equal to Vi cos beta into cos beta phi minus cos beta divided by k into RB into dm upon d theta. So, ratio of true power to actual power will be cos phi divided by cos beta into cos phi minus beta. So, the correction factor for lagging power factor load is your cos phi divided by cos beta into cos phi minus your beta. So, error in the wattmeter reading will be actual wattmeter reading minus 2 power. So, that will be 1 minus cos phi divided by cos beta into cos phi minus beta into actual wattmeter reading, and that will be equal to approximately 1 minus cos phi upon cos phi minus beta into actual wattmeter reading. So, error in the wattmeter reading will be tan phi into tan beta into 2 wattmeter 2 power, or we can say all error in wattmeter will be equal to V I sin phi into tan beta. So, this note this error is considerable at low power factor. So, for compensation for inductance of pressure coil, the error due to the pressure coil inductance is compensated using the capacitor. A capacitor is connected in parallel to the portion of multiplier, and total impedance of the circuit is now shown in the figure. So, it will be ZP equal to RP minus R plus j omega L plus R into parallel with the minus j omega upon C, that is R minus j upon omega C, and this will be ZP equal to RP minus R plus j omega L and plus this the parallel impedance of this your R and omega C. So, R into minus j upon omega C, that is R minus j upon C. So, proper selection of circuit constant at power frequency, that is omega square C square R square is much less than 1. So, we can say Z equal to RP minus R plus j omega L minus plus R minus j omega C R square, or equal to RP plus j omega L minus C R square, or we can say if L equal to C R square, then ZP will be RP, or you can call it beta will be 0. So, that is the only by putting this kind of compensation we can say ZP become RP and beta angle becomes the 0. So, now coming to the error due to the pressure, that will give you the compensation properly and you will get the right reading. So, now coming to the second, the error due to the pressure coil capacitance. So, we can say mainly due to the interturn capacitance of series resistance, the wattmeter reads low or leading power factor of the load, and the error due to the method of connection. So, if the load is small in like a figure A, connection is huge, the pressure coil is connected directly to supply and current coil in series with the load, and second connection is the pressure coil connected across the load and current coil in series with the line. So, for a large load connection is similar to the shown B. So, now coming to compensation of error, the use for large current and low power factor, that is shown here, that the pressure coil connected across the load. So, compensation coil is connected in series with the pressure coil circuit, and if opposes the field of current coil as you are seeing just here. So, error caused by pressure coil current is neutralized. Now, coming to error of your eddy current errors. So, solid metal parts should be avoided as far as possible to reduce the eddy current error, and error due to mutual inductance effect. So, caused due to the mutual inductance between the current and the pressure coil of the wattmeter. So, these errors are quite low at lower frequency, but they increases with become more as frequency increases. Now, coming to stay magnetic field error. So, this electrodynamometer wattmeter has a relatively weak operating field. So, the stay loss is serious error, and the instrument should be shielded against the effect of stay magnetic field. Now, coming to the 7, the error caused by vibration of moving system. So, vibration not only make the position of the pointer difficult to read, but also to mean position of the pointer may be displaced from the corresponding to the average value of power. So, these vibrations are avoided by designing the instrument in such that the natural frequency of the moving system must be less than the twice of frequency of the system on which the wattmeter is intended to be used. Now, coming to a temperature error. So, the reading is affected by the change in the room temperature because of the change in resistance of the pressure coil and stiffness of the spring. Now, coming to advantage disadvantage of this electrodynamic wattmeter. The advantage are they have a precision grade accuracy, and these instruments can be used both AC and DC, and they are also used as transfer instrument. And disadvantage, they have a non-uniform scale, and secondly they are more expensive than either of PMMC or MI type of instrument. The third advantage, electrodynamic voltmeter are very useful where accurate RMS value of voltage and irrespective of waveform are required, and these instruments are also free from hysteresis losses and eddy current losses. Disadvantage, these instruments are sensitive to overloads and mechanical impact, and therefore, they must be handled with great care, and these instruments have a low sensitivity due to the low torque to weight ratio. Now, coming to another kind, induction type of wattmeter. So, here this work on a same principle as induction ammeter and voltmeter. So, use only for AC power measurement, this induction type of wattmeter. As you can see here, like how it is the arrangement, total arrangement of the total supply and circuitry is there. So, coming to the construction of this wattmeter, the instrument consists of two laminated electromagnets, and shunt magnet coil is excited by current which is proportional to the load voltage called pressure coil, and the series magnets coil is excited by load current, or definite it is also current coil. So, coils in on series are also wound that they magnetize the core in same direction. So, central limbs is provided with the copper shading band, so that the shunt magnet flux lag exactly 90 degree behind the applied voltage. Now, coming to a thin aluminum disc is mounted on a spindle and is placed in between the two magnets coil, so that it cuts the flux of both the magnet, and a spring is used to provide the controlling torque. Eddy current damping is used here. So, unlike the dynamometer type instrument, the pressure coil of a induction wattmeter is made of as inductive, so that the shunt magnet flux lags the applied voltage by nearly 90 degree. So, now coming to the principle of operation of this induction type of wattmeter. So, alternating flux is produced by shunt and series magnet, and flux produce eddy current, eddy induced EMF in the aluminum disc which causes the eddy current, and deflecting torque is produced by because of the eddy current interaction with the fluxes. Now, coming to the basic theory of it. So, deflecting torque is T d equal to k V I cos phi, that is k 1 into p, and controlling torque is T into k theta. So, at the equilibrium T d equal to T or theta equal to k 1 upon k into p, or theta is proportional to p. So, scale nature of the induction type of wattmeter is uniform in nature. Now, coming to advantage and disadvantage. Advantage is large deflection torque, unaffected by stray magnetic field, robust in construction, and uniform scale. And disadvantage is heavy moving system, less accurate, high pressure consumption, and used for only AC load. Now, coming to typically 3-phase power measurement. The measurement of power in 3-phase circuit can be like a single or one wattmeter method if load is connected, balanced load is connected delta star, or 2 wattmeter method where load or connected delta or star, or 3 wattmeter and load is connected delta and star. Now, coming measurement in 3-phase circuit. So, for star connected load we can say VL equal to root 3 times V phase and IL equal to I phase, and VR V 3-phase voltage equal to V phase, and typically VRY VIR VBR equal to VL, or VI equal to VR minus VY, and VYB equal to V minus VB, and VBR equal to VB minus VR. And however, in delta connected load IL equal to root 3 I phase and VL equal to V phase, or IRY RYB and IBR equal to I phase, and IR RY IB equal to IL, and RY equal to IR minus IB, and YB equal to I minus IB, and IBR equal to IB minus IR. So, for any load star or delta connected, the 3-phase total power is P equal to root 3 VL IL cos phi, or equal to 3 V phase I phase cos phi, where phi is the power factor angle. So, coming to first 1 wattmeter method to make a 3-phase power measurement. So, reading here will be the wattmeter is connected like a per phase, in the sense current coil is connected in series with the 1 phase load, and pressure coil connected between neutral and one particular phase in 3-phase balance supply with connected balance load. So, here the wattmeter reading will be VRN into IR into cos of angle VRN IR, and that will V phase I phase into cos phi. And when you want to make a total power for 3-phase, so P will equal to 3 V phase I phase cos phi equal to 3 W, that is per phase power. So, now coming to in case of delta connected load, the wattmeter reading is now here wattmeter is connected in your one of the phase with the current coil and pressure coil across the line, that is phase voltage. So, and W will be V by B I by B cos V by B and I B angle between the two, and this will be equal to V phase I phase cos phi, and the total power will be equal to P equal to 3 phase I phase and cos phi, that is 3 W. and this is the typical connection and phasor diagram of respective of delta connected load. Now, coming to one wattmeter method, the disadvantage is applicable only for balanced load. For star connected load, neutral point must be available, and for delta connected load must be possible to open the closed delta, not possible in many load. So, now coming to 3 wattmeter method. Virtually this 3 wattmeter method applicable for both balanced and unbalanced load. So, true power in is the summation of all 3 phase wattmeter reading, W equal to W1 plus W2 plus W3, and 1 wattmeter and 3 wattmeter method rarely used in an industrial load, and you can see how the pressure coil is connected typically between line to neutral and your current coil in current in series. And in delta connected, of course, you have a pressure coil connected across line, that is phase voltage, and current coil is connected in series like. So, now you can say in case of 2 wattmeter method, the Blondel theorem says it is a common point is located on one of the line, the power may be measured by n minus 1 wattmeters for n phase system. So, based on that, on Blondel theorem, we can say 2 wattmeters can be used for measurement of 3 phase power. Now, coming to for a case of a star connected load, I mean you can see the connection here, that we are connecting a like a current coil in line with the 2 line for W1 and W2, but pressure coil is connected with that line and with the third line means RB, or in second case it is YB. So, current coil is connected in any of the 2 line, and voltage coil is connected between its own current coil terminal and the line without a current coil. And if W1 and W2 are the 2 wattmeters reading, then the total power W equal to W1 plus W2. Now, coming to typically for this star connected load, we discussed 2 wattmeter readings are W1 from phasor diagram, we can say IR. Here I mean like you have a current IR which is here into V by VRB, that is the voltage virtually here, into cos angle between IR and VRB, and W2 will be IY V by B, and angle between IY and the angle between your IY and YB. So, from the phasor diagram, this angle of RY and YB 30 minus phi. So, W1 will be IR V by RB cos 30 minus phi, or VLIL cos 30 minus phi. So, now coming to angle between IY and YB, say 30 plus phi, that is virtually this angle. Here it was typically this angle. So, you can call it W2 will be IY YB equal to cos 30 plus phi, or IL VL cos 30 plus phi. So, now hence total power will be equal to W1 plus W2, that you can say W equal to VLIL cos 30 plus 30 minus phi, or plus cos 30 plus phi, and this will be 2 VLIL cos 30 into cos phi, that will be root 3 VLIL cos phi, or 3 VP IP cos phi. Now, coming to delta connected load, when coil connected in any of the 2 line, and voltage coil is connected between its own current coil terminal and the line without a current coil, and if W1 and W2 are the 2 wattmeter readings, then we can say total power W is equal to W1 plus W2, and 2 wattmeter reading will be here W1 equal to R IR again from phasor diagram into VRB into cos of angle IR into VRB in the same manner, and W2 will be IY VRB, that is cos IY into and angle between IY and V by B. So, from phasor diagram we can say angle between IR and VRB is 30 minus phi. So, W1 will be IR VRB equal to cos 30 minus phi, and or equal to VLIL cos 30 minus phi. So, similarly, angle between IY and V by B is 30 plus phi, and wattmeter 2 reading will be W2 equal to IY VR by YB, that is cos 30 plus phi, or VLIL cos 30 plus phi. So, the total power W will be W1 plus W2 equal to W VLIL in bracket your cos 30 minus phi plus cos 30 plus phi. So, that will become a 2 VLIL cos 30 into cos phi, and that will be equal to root 3 VLIL cos phi, or equal to 3 V phase I phase cos phi. For star or delta connected lagging power factor load, so we can say W1 is VLIL cos 30 minus phi, and W2 is VLIL cos 30 plus phi. And for star or delta connected leading power factor load, it will be like your W1 VLIL cos 30 plus phi, and W2 will be VLIL cos 30 minus phi. So, now for star delta unity power factor load, cos phi will be 1 and phi equal to 0. So, W1 equal to W2 equal to VLIL into cos 30. Now, coming to advantage and disadvantage of 2 wattmeter method. The advantage are applicable for balanced as well as for unbalanced load. Neutral point of star is not necessary, delta load need not to be open, cost is a cost effective and power factor can be obtained, and total reactive power can be determined. Disadvantage not applicable for 3 phase 4 wire system, and sign of W1 W2 must be identified. So, now you can call it the for balanced lagging power factor load, W1 equal to VLIL cos 30 minus phi and W2 equal to VLIL cos 30 plus phi, and total power will be W1 plus W2 equal to root 3 VLIL cos phi, and also W1 minus W2 will be VLIL sin phi. So, using these two equations, W1 upon W1 minus W2 divided by W1 plus W2 will be VLIL sin phi divided by root 3 VLIL cos phi, that become tan inverse divided by tan phi divided by root 3, and or tan phi will be root 3 into W1 minus W2 divided by W1 plus W2, and phi is tan inverse here root 3 W1 minus W2 divided by W1 plus W3, and power factor cos, that is cos phi will be cos inverse tan inverse root 3 W1 minus W2 divided by W1 plus W2. So, now you can say variation of 2 wattmeter reading with the power factor. You can say if we go from typically from your 90 degree leading to lagging. So, we go from leading power factor starting for 90 degree, it will be your typically 0, and on lagging also it is 0, so it is approaching 1, and these 2 wattmeter how it is changing with it similar to like a sine cosine waveform, and typically you can call it at angle 0 at unity power factor, both power meter reading will be equal W1 equal to W2 as you can see here like. So, we can say power factor calculation by 2 wattmeter method has a following 5 conditions. So, range of power factor when cos phi equal to 0, phi equal to 0, cos phi equal to 0, and phi equal to, you will have a one reading positive, another reading negative, and when that is your lagging or you can call it lagging or leading power factor, but power factor is 0, and when your power factor is 0 to 0.5, angle is between 90 to 60 degree, and one reading is positive, another is negative, and third condition when cos phi equal to 0.5, that is phi equal to 60, one reading is positive and another reading is 0, and when you have a power factor 0.5 to between 0.5 to 1 or 0 to angle is 60 degree to phi equal to 5 is between 60 to 0, that is both reading are positive, and when cos phi equal to 1, phi equal to 0, both reading are positive and equal. So, these are the different conditions which are applicable for different kind of power factor of load. Now, coming to reactive power measurement by 2 wattmeter method. So, we can say apparent power S equal to root 3 VLIL in VA or kVA, and active power is P equal to root 3 VLIL cos phi, that is W1 plus W2 watt or kilowatt, and reactive power is root 3 VLIL sin phi, and that you can say root 3 V1 W1 minus W2 VR or kVR. Now, you can say in 2 wattmeter reading, as you can show the diagram here, we can say W1 is equal to VLI cos 30 minus phi, and W2 is equal to VLIL cos 30 plus phi, and W1 minus W2 equal to VLIL sin phi, and total reactive power is equal to Q equal to root 3 VLIL sin phi, and that is equal to root 3 W1 minus W2 VR. So, coming to reactive power measurement by 1 wattmeter method. So, in the case you can see 3 phase balanced load either star delta connected. So, current coil we are connecting in one phase and pressure coil we are connecting other 2 phases. So, we can say AC watt reactive power of 3 phase AC is calculated by 1 wattmeter method, and for figure we can say W equal to I into VPC cos angle between IC and VPC, and or we can say IR by B V by B cos inverse I angle between IR and V by B, and from the phasor diagram we can say angle between IR and V by B. From phasor diagram this angle is equal to 90 minus phi, or so wattmeter reading IR Y V cos 90 minus phi or equal to IL VL equal to sin phi, or we can say total reactive power Q will be root 3 times wattmeter reading in VA or kVR. So, now coming to energy measurement. So, this if the total power delivered consumed over a time, that we call it energy, power multiplied time, and we can have a single phase energy meter connections as it is shown here. We have a input connection coming out and we have a 2 terminal going to be out the load with the breaker between night and neutral for single phase load. So, we can say joule or watt second, 1 watt over an interval of 1 second. So, energy absorbed or supplied by the enablement from time t 0 equal to t is W equal to from t 0 to t p dt or t 0 to t v I dt. So, you can say electric power utility company measures the energy in watt hour, and that is 1 watt hour equal to 3600 joules, and measuring instrument of energy. So, we get single phase induction type of meter, polyphase energy meter, digital energy meter. So, coming to single phase your induction type watt meter. So, here you have a induction type of energy meter are universally used for the domestic and industrial application. You can see the connection of a induction type energy meter. We have an input terminal and we have output supply terminal going to the load, and of course, it is given the connection on the face of this energy meter. It works on the principle of induction, and eddy current induced in the moving system interact with each other to produce a driving torque, due to which the disc rotated to record the energy. So, it is a basic principle is here. So, you have a like a pressure coil on a core and you have a current coil on the core, and in between you have a typically aluminum disc, rotating disc, and that you have a gear for the dialing to show the to record the number of, and you have magnetic brake, and you have a current typical current coil with a copper shading coil. So, it is interlock structure of with the outer layout of the energy meter, as you can say here. So, you have a disc here which is shown here, and you have all the readings with the disc typically traced for the dial, that how many rounds it make like. So, it consists of mainly 4 parts: driving system, moving system, braking system, and registering system. So, typically all 4 parts are shown here. So, now you can see how it looks like. You have a pressure coil and you have a copper shading also here, then you have a aluminum disc, we have braking mechanism, and on the other side you have a typically a current coil over the magnet. Here you have pressure coil over another electromagnet like, which you make with the help of that. That is the structure of induction type of energy meter. Now, coming to typically, as you can see here, the similarly the diagrams that you have a disc with the graded dial to grading train of 2 dial, and this is your typically voltage coil on the one core, on other side core you have a current coil. So, you have a driving system, series and shunt magnets are used, and copper shading bands to bring the flux exactly in the quadrature with the voltage coil. And moving system, the aluminum disc is mounted in between the 2 magnets, and pivot and jowl bearings arrangement for support. So, now coming to braking system, a magnet near the edge of aluminum disc, and braking torque can be adjusted by varying the position of magnet. And resisting mechanism, it records the number of the revolution made by the aluminum disc, as you can say in the recording with the linear, then dividing the mechanism. So, you can say what is the typical theory and operation of it. So, shunt magnet produces alternating flux phi or phi sh, and phi s or phi ac is produced due to series magnet, and each portion of magnet experiences some force due to the motoring action, and phi s and phi p are directly proposition to the currents in the series and parallel respectively. And you can say 2 torque opposite to nature are produced because of the eddy current, which produced by the series and parallel coils, as you can see here, and the net torque produced is the difference between the 2 torque. So, now basic theory is the torque due to IES equal to T proportional to phi p into IES into cos phi p with angle between phi p and IES, or you can say angle between phi p and IES is alpha plus phi, and the torque due to IES is your T 1 equal to phi s IES cos angle between phi s and IE, and that angle phi s is 180 minus phi plus alpha, and then you can say the net torque will be T d proportional to T 1 minus T 2, and that will phi p IES cos phi plus alpha minus phi s IE x p cos 180 minus phi plus alpha, or phi is where the phi p is proportional to V and phi s is proportional to I, and I is proportional to phi s, and phi is proportional to I, and I is E p proportional to phi p proportional to voltage. So, we can say T d is proportional to K 1 into V I cos phi and if delta is considered, then T D is V I sin delta minus phi. So, delta is achieved to be exactly 90 degree with the help of copper shading bands. So, it will become, because of this, again V I cos phi. So, at the steady state, T D equal to T B breaking torque. So, K 1 V I cos phi equal to K 2 n, and n will be equal to K phi cos K V I cos phi, and or n equal to K into power. So, number of revolution is now 0 to T n dt, or equal to 0 to T K into power into dt, or K into energy. So, now the K is the meter constant and is given as K equal to n upon energy, or number of revolution per kilowatt hour, and the number of revolution of the disk per kilowatt hour of energy consumption called the meter constant. Now, coming to typically here, and this single phase induction type of whatever meters, the error and adjustment. So, there is a lag adjustment of power factor arrangement used to adjust the phi equal to 90 degree. So, phi turns of thick wire is placed, and also called quadrature adjustment of inductive adjustment. Then now coming to like a light load adjustment or friction adjustment. So, shading loop is provided between the central limbs, and you can say L 2 is called light load plate, and we say shading loop can be moved laterally to adjust the speed to provide the necessary compensation. Now, coming to third is a creeping adjustment. So, disc rotates slowly and continuously even at no load. So, due to the frictional overcompensation. Now, fourth is like overload compensation. So, when the disc rotate in the field of series field under the load conditions, so EMF is induced in this disc, and the produced eddy current is interacted with the series flux and produce self breaking torque. At high current, self breaking torque is high, causes the series error, and an overload compensation device is shown in figure is not for overload compensation. So, now coming to voltage compensation, the voltage compensation is provided by the saturable magnetic shunt, and for temperature compensation, a special magnetic material such as mu temp is used for the temperature compensation and does not allow the disc to rotate faster as temperature increase. Now, coming to advantage of simple and strong construction. Second is cheap, higher torque to weight ratio, then more accuracy, less maintenance, and range can be extended. A disadvantage can be used only for AC circuit, creeping cause errors, and lack of symmetry in magnetic circuit cause error. Now, coming to typically theoretical problem. What is the need of providing copper shading band on the pressure coil magnet of induction type of machine in order to cause a resultant flux in shunt magnet to lag the phase by exactly 90 degree behind the applied voltage. So, that is one or more copper rings known as copper shading bands are provided on one limb of the shunt magnet. Why to use the aluminum disc preferred over a copper disc energy meter? An aluminum disc is usually preferred to a copper disc in order to have resistance per unit watt is smaller. What is the creeping in motor type energy meter? In some energy meters, the disc continue to rotate when potential coils are excited, but no current flows. This effect is known as creeping. And how with the controlling torque provided in power magnet instrument? In power magnet instrument, controlling torque is provided by the two phosphorus branch hair spring, either helical or spiral coiled in the opposite direction, normally equal to strength. Now, coming to question 5, name the methods used for power measurement in 3 phase, like single wattmeter, 2 wattmeter method, 3 wattmeter method. How voltage coil is connected in induction type of meter? It is connected in parallel to the supply and load. How the current coil is connected in induction type of energy meter? It is connected in series with the load. Nature the error caused in dynamometer wattmeter, error due to pressure coil inductance, error due to pressure coil capacitance, error due to the methods of connection, error due to the electromagnetic field, and error due to eddy current. Now, coming to we solved numerical problems. So, coming to first numerical problem, the line to line voltage of 3 phase 50 Hz AC circuit shown in figure is 100 volt RMS, assuming that the phase sequence is R by B, what will be the reading of 2 wattmeter. So, coming to VLL 100 volt, ZPH is 5 ohm at the angle of 60 degree, and where phi is 60 degree. So, as 4 star connected load, V phase equal to VLL by root 3, that is 57.735, and I1 equal to V phase upon Z, that is 57.735 divided by 5, that is 11.547 ampere. Now, wattmeter reading 1 reading will be W1 equal to I phase, V phase I phase cos 30 minus 5. So, that is 57.735 into 11.547 into cos minus 30. So, it comes 999.99 watt, and wattmeter 2 reading W2 is V phase I phase cos 30 plus phi, that will be 57.735 into 11.547 into cos 90, that is 0 watt. Now coming to second example, while measuring the power of 3-phase balance load by 2 wattmeter method, the reading are 100 watt and 250 watt. Calculate the power factor of the load. So that is phi equal to tan inverse root 3 W1 minus W2 divided by W1 plus W2, and that equal to tan inverse root 3 250 minus 100 divided by 250 plus 100, or tan inverse root 3 0.4285. This is 36.5 degree, and power factor cos phi, that is cos 36.5 degree, that is 0.803. Now coming to example 3, a 3-phase 10 kVA load has a power factor of 0.343. The power is measured by the 2 wattmeter method. Find the reading of the each wattmeter. Power factor is leading, power factor is lagging. So coming to S equal to 10 kVA, cos phi equal to 0.342. So S equal to root 3 VLIL. So VLIL is 10 into 10 to the power 3 by root 3. So that is 5773.502 VA. And for leading power factor, cos phi equal to 0.342, phi is cos inverse 0.342, that is phi equal to 70. So wattmeter 1 reading will be W1 VLIL cos 30 plus phi, that is 5073 into 0.502 into cos 30 plus 70, that is minus 1002.5582, and wattmeter 2 will be W2 VLIL cos 30 minus 70, that is 5773.4027 cos minus 40, that is 4422.759. Now for lagging power factor, wattmeter reading 1 will be your W1 equal to VLIL cos 30 minus phi, and that your 5773.502 into cos 30 minus 70, that is 4422.759, and W2 wattmeter 2 reading W2 VLIL cos 30 plus 70, that is 577.4027 cos 100, that is minus 1002.558. Now coming to example 4, 2 wattmeters connected to measure the input to a balanced 3-phase circuit indicating 2000 watt and 5000 watt respective. Find the power factor of the circuit if both the wattmeter are positive and the latter is obtained after reversing the current to the one of the instrument. So both reading positive means W1 2000, W2 500. So cos inverse cos phi equal to cos inverse cos into tan inverse root 3 W1 minus W2 divided by W1 plus W2, and cos phi will be again cos tan inverse root 3 2000 minus 500 divided by 2000 plus 500, or cos tan inverse 1.0392 or 0.6933 lagging. And when we obtain W2 by reversing the connection of, hence W2 is negative. So W1 is 2000 and W2 minus 500, and cos phi equal to cos into tan inverse root 3 2000 minus in bracket minus 500 divided by 2500. So it becomes cos tan inverse 2.8867 or 0.3273 lagging. So coming to example 5, energy meter is designed to make 100 revolution of the disk for 1 unit of energy. Calculate the number of revolution made by it when connected to a load of 20 ampere at 230 volt at power factor 0.84 an hour. If it is actual, makes the 360 revolution, find the percentage error. So I equal to 20, V equal to 230 volt, power factor 0.8 and T is 1 hour. So meter constant is your 100 revolution per kilowatt hour. So true energy is ET equal to VI cos phi T, that is 230 into 20 into 0.8 3600, that is 32.248 into 10 power 6 joules or watt second, or you can say 13.248 into 10 power 6 divided 3600 10 power 3 kilowatt hour or 3.68 kilowatt hour. Now number of revolution 360, so measured energy EM equal to 360 by 100, that is 3.6 kilowatt hour, and percentage error is sin 86 minus 0 minus cos 0 divided by cos 0 into 100. So error is minus 0.2436%. Now coming to example 6, a correctly adjusted 240 volt induction type wattmeter has a meter constant of 600 revolution per kilowatt hour to determine the speed of the disk for a current of 10 ampere at a power factor of 0.8 lagging. If the lag adjustment is altered so that the phase angle error between the flux and applied is 86 degree, calculate the error introduced at unity power factor 0.8 lagging power factor. So energy consumed in 1 minute is equal to VI cos phi into T, that is 240 into 10 into 0.8 divided by 160. So that comes 0.032 kilowatt hour. Now number of revolution in 1 minute is your 0.032 2 into 600, that is 19.2 rpm, and speed of the disk is 19.2 rpm. When lagging adjustment is altered, that is the speed n equal to kV I into sine delta minus phi, delta is 90 degree for correct axis. So, for unity power factor phi equal to 0, error will be sine 86 minus 0 minus cos 0 divided by cos 0 into 100, that becomes minus 0.2436%. And for 0.8 lagging power factor phi equal to 60 degree, percent error is sine 86 minus 60 minus cos 60 divided by cos 60 into 100, that becomes minus 12.326%. It means for lagging power factor it has a more error like. Now, coming to example 7, a 230 volt single phase watt meter. Watt hour meter has a constant load of 4 ampere passing through it for a 6 hour at unity power factor. If the meter disk makes 2208 revolution during this period, what is the meter constant in revolution per kilowatt hour? Calculate the power factor of the load if the number of revolution made by are 1472 when the operating at 230 volt, 5 ampere and 4 hour. So, V equal to 230 volt, I equal to 4 ampere, power factor is 1 and T equal to 6 hour. So, energy consumed V I cos phi into T, that is 230 into 4 into 6, that is 5.52 kilowatt hour, and meter constant is number of revolution per kilowatt hour, that is meter constant 2002 0 divided by 5.52, that is 400 revolution per kilowatt hour, and at meter constant 400 revolution per. So, K equal to revolution about energy consumed. So, that is equal to 1472 divided by 400, that is 3.68 kilowatt hour, and energy consumed G equal to V I cos phi into T, that is cos phi equal to E upon V I T T, that is 3.68 divided by 230 into 5 into 4 into 10 power minus 3, that is cos phi equal to 0.8. And there are some unsolved numerical problem. So, you can solve in the similar line as we discussed already the solved problem, and these are the references from which we have developed this material, and thank you very much.